Hey everybody, it's Mr. N here, and we are going to do this little review on area and volume, and these volumes will be solids of revolution. So let's take a look at this first one and get started here. This first one says, find the area bounded by each curve. And this first one is y equals the cube root of x and y equals the square root of x. Now, the first thing we should always do is always sketch a quick graph to see what we're looking at. So in this case, we're looking at this situation where we've got the y equals the cube root of x going up like this, and the square root of x kind of coming through like this at that curvature. So that's kind of zoomed in a little bit because I'm going from 0 here and they intersect at 1. And you could tell that they intersect at 1 because when you put the values in, that'll happen. They'll intersect at 1, 1. Alright, so remember how we do these. Now we're going to say the top curve minus the bottom curve for the area, or you can go the right curve minus the left curve. Just remember, if you go top minus bottom, look at the way I'm drawing this. These slices are dx, so the thicknesses is dx. If you do it from left to right, like this has a thickness of dy. So then these equations would need to be in terms of in terms of y. So x equals something y. But we're going to go ahead and stick to this method right here and make our slices dx, and we're slicing it all the way from 0 to 1. So the area under that curve is going to be from 0 to 1, the top minus the bottom curve, dx's, because those are my slices. So the area is 0 to 1, and the top curve is going to be the cube root of x. The bottom curve will be the square root of x, dx. This ends up equaling the integral from 0 to 1. And I'm going to rewrite this to be x to the 1/3 minus x to the 1/2 dx, 0 to 1. Actually, let's go ahead and integrate this at this point. So let me get rid of that. And we are going to just go ahead and integrate it at this point, and I'll put this down here. The area equals, this is going to be 3/4 x to the 4/3, minus, this will be 2/3 x to the 3/2, because we're raising it up 1. Yep. On the bounds from 0 to 1, we end up with 3/4 minus 2/3, and this ends up being common denominator 12, so 8, 9, so 9 minus the 8 will give me 1, so this will be 1/12 square units. Alright, moving on to number 2. For number 2, let's again take a look at it. We've got these two curves, the cube root of x minus 3 and 13 minus x. So sketching a quick graph. Now I sketched the graphs ahead of time, so obviously you want to make sure you get these graphs correct. We go from 3 here, and this x cubed one kind of goes like this, and then this is a line, so it's going to come out to 13 right here. And the x, that's where it'll cross. Those will be the intercepts. Now we need to find what that point is right there. And you can almost kind of take a look at this and determine, okay, think about it. The cube root, it's got to come out to be something nice. So if I chose 11, 11 minus 3 gives me 8. The cube root is 2, so that's 2. And look, 11, y would be 2, so 11. This problem was made to work out nice. Now, if it didn't work out this nice, obviously you can use your calculator to find that point of intersection, set them equal to each other, and solve it mathematically. Either way. All right, so now, I'm going to show you this problem in 2 methods. We're going to go ahead and do, if I did this with vertical slices, let's get some vertical slices in here, and if I did this like this, notice I'm using one equation here. I'm using this cube root x minus 3 all the way to this point, and then it changes. Now my equation changes to be the 13 minus x, that one. So I have 2 regions here if I slice these as dx's. So let's try it that way, and then we'll try a horizontal approach. So let's first do method 1, dx, because I'm taking vertical slices. All right, well, over here I have two regions. I have the area is going to be from 3, the integral from 3 to 11 of region 1, plus, actually we can color coordinate this, so the area will be the integral from 3 to 11 of region 1, then we'll say plus from 11 to 13 of region 2. All right, region 1 is going to be the cube root of x. So the area will be from 3 to 11, and this is going to be the cube root of x down to here minus 0. So it'll be the cube root of x minus 3 minus 0 because we're coming down to the axis dx plus, and in region 2 we end up with the integral from 11 to 13 of 13 minus x dx from the top to the bottom there. All right, so region 1, we're going to go ahead and integrate that, and in region 1 we're going to get, this will be 3/4 because it's x to the 1/3, so that's going to be 4/3 when I raise it up, so I need a 3/4 out in front. Again, if you're having trouble with any of these integration techniques, just maybe practice substitution. You could do u substitution on this one if you'd like, but this one you should be able to get. So it's to the 1/3, so I have to raise it up a power, so that becomes 4/3, and I need to eliminate that, so I'm just kind of taking the derivative in my head to check myself as I do this through a guess and check method. So we'll get x minus 3. This is 4/3 on the bounds from 3 to 11. Plus, this one ends up being 13x minus 1/2 x squared on the bounds from 11 to 13. Let's finish this up here. All right, so for the first one, I'm going to plug in 11. I get 8. 2, take the cube root of that, I get 2, and then raise that to the 4th, and then multiply it by 3/4. So I'll end up with 12 minus 0, because when you put in the 3, you get 0. So the area is going to be 12 minus 0 for that first part, and I did most of that in my head, so be careful. Write it out if you need to. And then the second part, 13 times 13, and minus 169, half of that. So you're going to get 84.5. Okay, minus over here you'll end up with 82.5. Okay, so then the area ends up being, actually let's do it in another color to finalize. The area will be 14 square units. Okay. Now let's look at this in another method. We're going to say method 2, and we are going to, I'm going to quickly sketch this again right here. We've got something that looks like this, and then that piece like that. That's at 3. This is at 11. This was at 13. This was at 2. And this time, this is kind of, let's get that curve a little bit there. This time, I'm going to take my horizontal slices, and if I take horizontal slices I end up with thicknesses of dy. So this will be the right curve minus the left, and notice if I did it this way I'm just going from 0 all the way up to 2, and I don't need to use two regions, but we need dy. So I need to take my equation and make sure that these are in terms of y. So the first equation, I'm going to solve this for y, so I will cube it, and I'll get x minus 3. So you end up with y cubed plus 3 equals x. For the second equation, just rewrite this, and you'll get x equals 13 minus y. So now the area is going to be the integral from 0 all the way up to 2, and remember I'm doing this as dy's, and it's going to be the right minus the left dy. So this is going to be 0 to 2. And this will be, the right curve is the 13 minus y. The left curve is going to be y cubed plus 3 dy. Cleaning this up, you get the area equals the integral from 0 to 2. And this will, when you combine like terms and everything, you'll end up with 10 minus y cubed dy. Let's integrate that, and we end up with 10y minus 1/2 y squared minus 1/4 y to the fourth on the bounds from 0 to 2. Plug the numbers in, you'll get 20 minus 2 minus 4, and you get 14 units squared. Same result. This was a much easier method because I only needed one region. All right, let's see what else we got here. Number 3, let's move this up and take a look. And for number 3, we have to find the area between these two. Now, this can get a little complicated, and let me explain to you why. In this problem, I never said keep it to a particular quadrant. So if you graph these, what ends up happening is this y squared minus 2y, this parabola, comes through here, kind of like this. Okay, I didn't quite draw it. Let's try to redraw it a little bit better. It's going to come out and come through like, come through like this. Boy, I'm just having a heck of a time here. Let's try that one more time. I'll give myself one more chance. We'll come out, come through. There we go. That's a little bit better, not much. And now the other equation, let's go ahead and do that in another color. This is a cubic one right here, and what's going to happen is it's going to come through at this point right up over here, and also through right here, but then it's going to intersect like that. You'll get a little sliver. I didn't draw that sliver so well down there, but you have a little sliver down here that ends up crossing. So you've got 1 point here, 1 point there. Now we can find all those points of intersection, and it's going to be a pain in the butt to do that. So let's try to do it anyway. So we're going to set these two equal to each other to find points of intersection. So 2y squared minus 2y equals 12y squared minus 12y cubed. 0 is going to be negative 12y cubed plus 10y squared plus 2y. 0 equals negative 2y. I'm going to take that out, and I end up with 6y squared minus 5y minus 1. Again, I'm looking for those points of intersection. So I have 0 equals 2y, actually negative 2y, and then this is going to be 6y plus 1, y minus 1. So you get y equals 0, negative 1/6, and at 1. So this down here is negative 1/6, that's a 0, and that's at 1. Those are the y values. Now, why am I doing the y values? Because look at the way these equations are set up. If I try to go top minus bottom, that would mean my slices would need to be vertical, which would be dx. That would mean I'd have to solve this for y and this one for y, and that ain't happening. It's just too complex. So we can't do it with dy's. So instead, what we have to do is we have to take our slices horizontal, and let's go ahead and use a different color to show you that. So we need to take our slices to be horizontal like this, right minus left, and go from this point to that point, from 0 to 1, right equation minus left equation, and those gives me dy. And then I got to do it for down here, right minus left. Notice how it switches, but those will also be dy's as well. A lot of times they will just tell you to find the one end up above the axis. They won't have you find the little sliver down below, but let's just do it because it makes this problem more complex. So the area is going to be this, we'll call this region 1, we'll call this one region 2 in here. The area is going to be the integral, equals the integral of region 1 plus the integral of region 2. So this will end up being, so now let's take a look at what this little sliver is. Well, let's do region 1. Region 1 is going to be from 0 to 1, this region in here. And it's going to be the right equation minus the left one, so that'll be 12y squared minus 12y cubed minus the left one. So let's just go region 1 separate. let's keep this. And then the left one is going to be 2y squared minus 2y dy. Okay. And then region 2 plus the integral, again, this was region 1, this will be region 2, plus the integral. Now, this goes from negative 1/6 to 0. And now the curves flip-flop, so you have 2y squared minus 2y minus the 12y squared minus 12y cubed dy. Okay? All right, so the area ends up being, all right, so in region 1, if we clean that up a little bit, we'll get the 0 to 1, and this will be FOIL, or distribute that and then combine like terms and all that good stuff. You're going to get negative 12y squared, y cubed, sorry, plus 10y squared plus 2y dy. And then region 2 will be from negative 1/6 to 0. And that one comes out to be 12y cubed. It's actually going to be the opposite of all of these in sign, minus 10y squared, since we're subtracting them different, minus 2y dy. All right. Let's go ahead and integrate all this and see what we end up with. So, integrating this side, you're going to end up with negative 3y to the 4th plus 10/3 y cubed plus y squared from 0 to 1. Plus, integrating the other one, you're going to end up with something similar, but again with opposite signs. So this will be 3y to the 4th minus 10/3 y minus y squared on the bounds from negative 1/6 to 0. All right, cleaning all this up, you end up with the area equaling, when you plug that in, you're going to get negative 3 minus 10/3 plus 1. And this will be plus, this will be 0 minus 1 over 4/32 plus 5 over 3/24 minus 1 over 36. And you end up with 4/3 plus 13 over 12/96, which is 1741 over 1296 square units. Wow. If you didn't have to do the sliver portion down here, let's outline that. If you did not have to do this little sliver portion right in there, let's use the arrow, right in there. The problem, you don't have any of this stuff right here, and it becomes a lot easier. You're just dealing with this part. So that little sliver portion makes it intense. All right, let's move on to the next problem on this page. And this one is a volume problem. Find the volume of the solid bounded by those regions. Okay, so let's take a look. Let's graph what we have. We have y equals x squared. X equals 2, so this is this bound. Here's the equation. And y equals 0 down there. So it's that region in here. We can kind of go like this to show you that it's the region in there. And then we're going to revolve this about the x-axis, okay? So it's going like that, in that manner. Well, remember, the volume is pi r squared h, which is the same as saying the integral of the area, so you could find the area and integrate that. That's just another way. And in this case, it's going to be equal to pi times the integral. Now we're rotating it this way. We want to take our slices to be perpendicular to the axis of rotation, so I need them to be dx's. So I'm going slicing them up in the x. Again, perpendicular to the axis of rotation gives me a thickness of dx. So we're going to slice it from 0 to 2, and it's going to be r squared dx. So remember, it's this radius, which is the area, basically. So now, working this out, we end up with pi 0 to 2, and this is going to be x squared minus 0, obviously, squared dx, which gives me pi from 0 to 2 of x to the 4th dx, which gives me pi times 1/5 x to the 5th on the bounds from 0 to 2. And then plugging this in, this will be 32 pi over 5 cubic units. Not too bad on that one. All right, let's move on to the next problem. And let's zoom in on this one a little bit here. So let me set this up so that we could take a good look at it. And number 5. Okay, for number 5, we are still finding the volume of these solids. That's what these problems are right now. And let's graph what we have here and take a look at this. So I'm going to sketch this graph, and we end up with a parabola that goes up like this, and then the line y equals x goes like that. This has been on an AP Calculus test, something similar to this. They like these little leaf type shapes. And what we're going to do about this one, we're going to revolve it about the line y equals 1. So the line y equals 1 is up here, and we're taking this and going like that. Actually, let's do this a little bit better so that it's actually kind of accurate. And this is at 1 right here. So the line y equals 1 is really like that, where these intersect. Okay, let's go ahead and take our slices to be perpendicular to the axis of rotation, because we're rotating this up. Perpendicular gives me dx's again. So the volume is pi r squared h, which is the integral of the area. Now look at what happens. This is a washer method, but I've got 2 radii here, and I'm shifted up off. So the first radii is going to be 1, this 1 minus that equation. That's going to be my bigger radius. The second one will be 1 minus, 1 minus this one right there, my smaller equation. And I always taught you too, one way to think of it, we put this in our notes, you're always going to say the line of rotation minus whatever your equation is. So that's basically what we're doing, and there's the visual for why it works that way. So the volume will be the pi times the integral from 0 to 1, because I'm slicing it this way, all the way out to 1 here for the dx's. And we're going to say 1 minus big R, which is just the x squared, minus 1 minus the little r. So this is 1 minus big R, this is 1 minus little r squared. So this will be 1 minus, and that's 2x minus x squared. Squared dx. Okay, so the volume ends up being pi. Now, I went ahead and I foiled all this and combined like terms and did all that good stuff for you to save you a little bit of time here. So foil this out, combine like terms, do all that, and you end up with negative x to the 4th plus 4x cubed minus 5x squared plus 2x dx. So the volume is pi. Now let's go ahead and integrate this. You get negative 1/5 x to the 5th plus x to the 4th minus 5/3 x cubed plus x squared on the bounds from 0 to 1, which end up being pi times negative 1/5 plus 1 minus 5/3 plus 1. So the volume ends up being 2 pi over 15 cubic units. All right, moving on. Number 6. Okay, here's our 2 equations, and let's graph this. We've got y equals x squared over 4. So this ends up being a parabola that's like this. I'm kind of exaggerating a little bit. The line y equals 1. We're going to go like this. And we're going to revolve this about the line y equals 2 right up here. We're going like that around that line. So it's this region in here, moving it up around there. All right. This is very similar to the last problem. The volume is the integral of the area, which we said is pi r squared h, right? Because it's a cylinder. So everything's a cylinder. Remember that? Okay, anyway, so we're moving up and around like that. So the volume is going to be pi times the integral. Now I'm taking my slices to be perpendicular to the axis of rotation. So I'm going to take these as dx's, and so that means I'm going to go from here to here. And that intersection will be at 2 right there. And you can kind of plug that 1 in right over here. 1 equals x squared over 4. 4 equals x squared, so x will be the 2 value. So that's how I got this point of intersection right there. So the volume is going to end up being the integral from 0 to 2 of the 2, this is going to be your big R, 2 minus that curve, so 2 minus the x squared over 4 squared. Remember, volume is going to be pi times the integral of big R squared minus little r squared. So that's our big R squared, minus now our little r squared is going to be this little r, that little guy, and that's going to be 2 minus 1 squared. Again, the way I said it as a shortcut in our notes is the line of rotation minus what you're doing, since it's above it. All right, so now the volume is going to end up being pi times the integral from 0 to 2, and we can FOIL all this out. This one is going to be 1 squared, comes out to be 1, which is kind of nice. This other part will be 4 minus x squared plus x to the 4th over 16 minus 1 dx. Okay, so the volume will be pi times the integral from 0 to 2, and this will be 3 minus x squared plus x to the 4th over 16 dx, which comes out to be pi times 3x minus 1/3 x cubed plus 1 over 80 x to the 5th on the bounds from 0 to 2. So the volume ends up being pi times 6 minus 8/3 plus 32 over 80. And this ends up being 56 over 15. And that's a pi, and that's cubic units. Okay, moving on to number 7. In number 7, let's take a look at what we got, and let's graph this again. We are graphing y equals 4 minus x and y equals 0 about the line y equals negative 3. So this time we've got this situation, and this goes like this, and this is at negative 2 here to 2, and it goes up to a height of 4. So that's what we're looking at, and we're going to take this and we're going to rotate it about a line down here at negative 3. So 1, 2, 3, there's negative 3, we'll say. Oops, negative 3. And we're going to rotate this like that. Okay, so the volume ends up being the integral of the area. And again, this time we have the line minus our rotation, or sorry, I shouldn't say line, I should say equation minus our line of rotation. Okay, so we've got the equation minus the line of rotation, and we're going to go perpendicular to the axis of rotation, so these are dx's. So the volume is going to be pi times the integral from negative 2 to 2, so our slices go all the way out to 2, from negative 2 to 2. And this is going to be 4 minus x squared minus negative 3 squared. Now, look, we have a little gap here. So we're going to have to take this, and we're going to, since we have a gap, we've got this next, we've got 1, and then it's going to end up giving me this little hole there. So I do need to use a washer here. It's this curve minus it, and then that curve minus it. Well, that curve is just y equals 0 right there. So 0 minus negative 3 squared. So you have a big R squared and a little r squared. Again, this is the big R. That's your big R. And this one right here will be your little r. So that's your little r, and the other one was the big R. Okay, working this out. So let's continue to do this problem and finish it up. Volume is going to be pi, and then this, cleaning all this up from -2 to 2, FOIL this out, clean it up, you end up with x to the fourth minus 14, these are dx's by the way, sorry, 14 x squared plus 40 dx. So the volume is going to be pi, and now let's integrate it. You're going to get 1/5 x to the fifth minus 14/3 x cubed plus 40x on the bounds from -2 to 2. And when all is said and done, this ends up being pi times 32/5 minus 1/12 plus 80 minus -32/5 plus 1/12 minus 80. And this ends up all being 1472 over 15 pi cubic units. Wow. All right, last problem. Let's get this done. So let's see what we're facing here. We've got y equals the square 2 times root x minus 1 and y equals x minus 1 about the line x equals -1. So let's again graph what we're looking at. So we have this situation, and for this one we've got, let's put it in another color again, and let's go ahead and use this green. We haven't used that in a while. So this is at 1 and it goes up like that. This other line is going to go like this. So they will cross up way up over here at 5. And how do I know that? You could set them equal to each other and find out. So that's one way to do it. Set them equal to each other. You can also kind of guess and check at it. 5 minus 1 is 4. Square root of that is 2. Times 2 is 4. So 5 minus 1 here on this side will be 4. So that works out. So that means this goes from 0 to 4. And this time we're going about the line x equals -1. So that's this line right here. So all of this is going to get rotated that way. All right, so we take our slices to be perpendicular to the axis of rotation. And then when we do that, that's perpendicular to it, we realize that they need to be dy's. So we need dy, which means I need x in terms of y, which means I need to solve both of these equations for x. So this becomes y over 2, square that, so, and then add 1, and that's what x is. So y squared over 4 plus 1 is the first x. And then the other one is just going to be y plus 1 is x. So now we've got a big radius and a small radius. And let's go ahead and outline, that's the big radius. That's the small radius right there. So we end up with the volume as the integral of the area. We have a big radius squared minus a little radius squared. So, well, the big radius squared is going to be my equation minus my line of rotation because it's to the left of it. So this ends up being, that's the y plus 1 minus your line of rotation, -1 squared. That's our big R squared. Minus little r squared. Well, that's going to be the y squared over 4 plus 1 minus 1 squared. So that's what I'm looking at, and these are dy's. All right, so this becomes, the volume is going to be pi on the bounds from 0 to 4. Oops, I forgot to put the bounds there. From 0 to 4 because we're slicing it vertically from 0 all the way up to 4. And this ends up being y plus 2 squared minus, this will be y squared over 4 plus 2 as well, squared, these quantities squared, dy. Okay, let's FOIL it out, combine like terms. Okay, FOIL all this out, combine like terms, I'll save you that hassle, and you end up pi times the integral from 0 to 4 of, cleans up really nice actually, 4y minus y to the fourth over 16 dy. So now let's finish this off. We are almost done. So let's go ahead and integrate, and we will get the volume equals pi times 2y squared minus y to the fifth over 80 on the bounds from 0 to 4, and that will end up as 96 pi over 5 cubic units. So hopefully this video has helped you set up these problems for volume and area and do the integrations and rotations and understand how it changes when we're not rotating about an axis. So hopefully this helped you. Good luck with area and volume, and make sure you subscribe.